Hi, I'm Byeongjoo. This paper describes a technique for producing a full surround or 360-degree 3D scan of an object using a structural light system and a kaleidoscope. Scanning the shape of the entire object in all its complexity is critical for many 3D applications, such as 3D printing, virtual reality, and augmented reality. To achieve full surround coverage, a single viewpoint is not sufficient. For example, consider this object where a small bunny is enclosed by a bunny-shaped mesh. It has intricate geometric features, including severe self-occlusions. As a result, we need a large number of diverse viewpoints to reconstruct this object in all its complexity. As the object shape becomes more complex, we can expect the number of viewpoints required for full surround coverage to become larger. This can be achieved by constructing light stages with multiple cameras and potentially projectors. However, such multi-view systems are typically costly and hard to build. A simple way to achieve a very large number of viewpoints is to surround the object with mirrors. It conveniently provides additional viewpoints without the need to move a camera or construct a multiple camera system. In particular, we use a kaleidoscope, which is a configuration of multiple planar mirrors. As we can see in the camera view, the kaleidoscope allows light to bounce around repeatedly until it hits the camera, and thereby combinatorially increases the number of viewpoints. With a kaleidoscope and a single camera, we can construct a virtual multi-view imaging system that is easy to build, calibrate, and deploy, with components that are easily available. However, can we directly use the kaleidoscopic system as a virtual multi-view system? To do so, we need the so-called label that is a virtual viewpoint associated to each pixel. I will show you an example of what the label is and why it is needed. Label is simply the sequence of meters that the ray back projected from the pixel encounters before intersecting the object. For example, consider this 2D kaleidoscopic system with 2 mirrors and a camera. The light path of the back-projected ray starts from the camera and hits mirror 1 and mirror 2, and finally hits the object. In this case, the label of the pixel L becomes 1, 2, which is the mirror sequence the back-projected ray encounters. Once the label is given, we can compute the virtual viewpoint using the geometry of the calibrated camera and mirrors. Then we can interpret this situation as the virtual camera is looking at the object. Therefore, once the label is given, the kaleidoscopic system can serve as a virtual multi-view camera system. The label is different for each pixel. Consider this example of another pixel. The back-projected ray follows a different light path, and the label in this case is 1, 2, 1. As each pixel segment corresponds to a different virtual camera, we need to identify the label of each pixel. We call this the labeling problem. By solving this problem, we can decompose the single captured image into multiple segments, one for each virtual viewpoint. Then a kaleidoscopic system can serve as a virtual multi-view system. But the labeling problem is not trivial because hundreds of virtual views are interwoven with each other as shown in the camera view. Even after the labeling problem is solved, we have another challenge. It is a correspondence problem between the virtual cameras. This is one of the main factors that degrades the quality of 3D reconstruction. To solve the correspondence problem, we add a projector to the imaging setup. We call this system kaleidoscopic structural light. The virtual viewpoint interpretation can be applied to the projector as well, so now we have virtual multi-view system with hundreds of projectors and cameras. Here is the pipeline of full surround 3D scanning using our kaleidoscopic structural light system. We first scan the object, and then label the virtual viewpoints of each pixel. Now this is equivalent to a light stage with hundreds of virtual projectors and cameras. So we can reconstruct a point cloud and a mesh. I will explain each step in detail. We first scan the object by turning on a projector pixel. This will illuminate a single 3D point on the object surface, either directly or after one or multiple reflections on the kaleidoscope. The illuminated point is observed at multiple camera pixels, each via a different sequence of mirrored reflections, and we save the location of these pixels. This provides us with a correspondence between a single projector pixel and multiple camera pixels, all of which also correspond to a single 3D point on the object. We accelerate our scanning process by turning on multiple projector pixels with a temporal code, which is similar to traditional structural light techniques. The key difference in the kaleidoscopic setting is the complexity of the epipolar produced by the multiple mirrors, which makes traditional column scanning schemes inapplicable. Instead, we randomly sample groups of 255 projector pixels, encode each pixel with an 8-bit binary code, and project the sequence of binary images that correspond to each bit of the binary code. Then we obtain the camera pixels corresponding to each projector pixel by decoding the binary code from the captured image. This parallel scanning technique accelerates acquisition, but also exacerbates interference, which means multiple projector pixels may illuminate the same 3D point, which could result in erroneous decoding. However, few decoding errors can be easily handled during the triangulation step later, using the constraint that all the camera pixels are originated from a single 3D point. From the scanning process, we obtain the correspondences between a projector pixel and multiple camera pixels. Now we need to solve the labeling problem to identify the virtual viewpoint corresponding to each pixel so that we can triangulate from this correspondence. We use epipolar geometry to solve the labeling problem. The key idea is, as the projector pixel and camera pixels in a correspondence are originated from a single 3D point on the object surface, the corresponding virtual projectors and camera should satisfy the epipolar constraint. So from the possible virtual projectors and cameras, we find the set that satisfies the epipolar constraint. Importantly, the fact that this search couples a single projector label with multiple camera labels greatly enhances the robustness of the labeling procedure. However, exhaustive search of all the possible set of virtual projectors and cameras is computationally demanding. It has exponential time complexity with respect to the maximum number of reflections. We introduce a computationally efficient approach. We reduce the search space by using the geometry of the mirrors, which has linear time complexity. Please refer to our paper for more detail. Our key result is to show that the epipolar labeling theoretically guarantees to provide unique and correct label. Consider this 2D example. We have a correspondence between the projector and camera via mirror reflections. The camera label is 2,1 and the projector label is 1. This should satisfy epipolar constraint, so our epipolar labeling will obtain this label. But is it the unique label that satisfies the epipolar constraint? Actually, there are another set of virtual projector and camera that has the same relative geometry and satisfies the epipolar constraint. This ambiguity happens when the labels are identically mirrored from the correct labels. For example, consider the virtual camera with label 212 and the virtual projector with label 12. Compared to the correct label, they have an additional reflection by mirror 2. In this case, each incorrect projector camera pair has the same relative geometry with the correct projector camera pair. This makes their epipolar geometry the same, and it makes an ambiguity in the epipolar labeling. However, this incorrect case can be rejected by using a simple additional constraint. That is, the reconstructed point should be inside the mirror system. We proved that this incorrect projector camera pair always produces the 3D point outside the mirror system. So the ambiguity by identically mirrored labels is resolved. There might be another random projector camera pair that also satisfies the epipolar constraint, but the chance of this is 0. because it is the probability of two arbitrary lines in 3D being coplanar. Using the epipolar labeling technique, we obtain the camera label and project label. For the visualization of labels, we sorted the mirror sequence in ascending order and color mapped it from magenta to cyan linearly. Now we know the virtual viewpoint corresponding to each pixel, so we can triangulate the point cloud from the correspondences. Then we reconstruct a mesh representation of the surface by using string Poisson surface reconstruction with PCA normals. To visualize the appearance of the reconstructed surface, we use a simple texture mapping procedure by projecting each vertex to all visible virtual cameras and computing the average intensity of the corresponding pixel values. As our setup uses a monochrome camera, we obtain per pixel color by projecting color channels sequentially from our RGB projector. We also visualize PCA vertex normals to help better assess the quality of the reconstructed mesh. Our system is able to reconstruct intricate shape with high accuracy and full coverage. We can reconstruct this highly complex elephant that fully encompasses another smaller object and has intricate geometric features, including concavities, a large genus number, and complex self-occlusion. We observe our system produces high-quality reconstructions for a variety of objects. In this example, the inner part of skeleton and the root of the mouse are visible only to limited viewpoints. But multiple virtual views of our kaleidoscopic system make it possible to reconstruct these occluded parts. Our system also reconstructs this test-shaped brush with full surround coverage that includes severe self-occlusions and concavities. The object that has the shape of the treble clef and skull are also reconstructed with full coverage. There are other kaleidoscopic imaging methods with different labeling techniques. For the comparison, we simulate the measurement of this 3D shape in the kaleidoscopic system and compare the results of each method. First, we compare our method with visual Hall technique. This technique solved the labeling problem in a passive illumination kaleidoscopic system by using space carving. The key idea of this method is the background pixels on the captured image do not intersect with the object, even after repeated mirror reflections. So the rays corresponding to those pixels can be back projected and carved. This provides a visual Hall of the object inside the kaleidoscope, which can be combined with ray tracing to obtain the label map. For objects with simple shapes that are predominantly convex, the labeling from a crude visual Hall is often a good approximation to the true labeling. However, for objects that have complex geometry and self-occlusions, the visual Hall invariably fails to capture concavities, especially when there are not enough background pixels. In this result, we observed that the visual Hall technique does not recover the inner bunny because of the limited background area available for space carving. As a result, the labeling deviates from the correct labeling. In labeling accuracy, green colors indicate correct labels and red color indicate incorrect labels. The labeling accuracy is 83% for the visual Hall method and 99.99% for ours. We also compare our method with time-of-flight camera-based method. This technique combines a kaleidoscope with a time-of-flight camera. The time-of-flight information provides the total path length from the camera to the object. This allows estimating the label and 3D point by folding the ray using the non-mirrored configuration. However, this technique requires a high-cost post-time-of-flight camera for precise time-of-flight measurement. In this comparison, we set the spatial resolution of the time-of-flight camera to be the same as that of our camera and simulate two different time-of-flight depth resolutions. The first one simulates a high-end LiDAR with a depth resolution of 0.2 millimeter, corresponding to the calibration error reported by the reference paper. The second one simulates a low-end LiDAR with a depth resolution of 5 mm, corresponding to a LiDAR of cost comparable to our setup. We observed that lowering the resolution results in a severe increase in noise in the reconstructed shape. Our technique achieves comparable results with the high-end LiDAR setup, while using a much more affordable imaging setup. We also quantitatively evaluate the performance of the various kaleidoscopic imaging methods. We use two metrics. The first metric is accuracy, which we define as the average distance of the vertices of the reconstructed mesh from the ground truss mesh. This metric quantifies how the reconstruction is close to the ground truss. Our method provides the best reconstruction accuracy. The second metric is coverage, which we define as the average distance of the vertices of the ground truss mesh from the nearest point of the reconstructed point cloud. This metric quantifies how well the reconstruction covers each part of the ground truss shape. Our method achieves comparable coverage with the high-end LiDAR setup. Our method has slightly lower coverage, partly because the points need to be visible both to projector and camera, while the time-of-flight setup has the co-located source and detector. There are some limitations in future work. First, the scanning time. We provide parallelized scanning techniques to speed up acquisition, but our scan times remain considerably longer than those achieved by traditional structural light acceleration techniques. Unfortunately, the complex nature of kaleidoscopic light transport makes these traditional techniques, such as column scanning, inapplicable to our setting. Second, the object size should be smaller than the kaleidoscope, so that it can be enclosed by the kaleidoscope. Although our prototype already scans the practical size of objects as large as 10 cm in diameter, we will need larger kaleidoscope to scan larger objects. Third, normal estimation. We use PCA normals for the surface reconstruction, but PCA normals can be inaccurate for shapes with complex topology, resulting in inaccurate meshes. Combining our technique with more accurate normal estimation procedures, including ones using shading information, can help improve the accuracy of the final mesh reconstructions. Last, VRDF reconstruction. Currently, we reconstruct only shape and use a simple texture mapping procedure to visualize the appearance of the surface. It can be improved by VRDF reconstruction, though the complex nature of kaleidoscopic light transport makes it hard to optimize the reflectance. Thank you for listening.